the slope of the tangent line. So this first statement I have here, it says the line tangent to the graph of f of x squared at the point 5, 2 has a slope of 10. We know the derivative is literally the slope of the tangent line. So all of those words we can simplify and just state that f prime of 5, that's the x coordinate, is 10. If I'm doing the Leibniz notation, looks a little bit different, but we can still state that the first derivative is 10. That's the value of the first derivative at a specific x point. We can also talk about the derivative as a function itself. So yesterday and the day before, when we were drawing out these graphs, we were sketching the function of the derivative, so we know that it is a function that we can actually graph. So another example is like if I say the derivative of f of x is x squared is 2x, we could also write that as just f prime of x is equal to 2x, or you can say the derivative d dx of x squared is 2x. Both of those statements that I just wrote down in green mean exactly the same thing. And then we haven't dealt too much with the second derivative except in terms of concavity. I can also state that the second derivative of x squared is 2. So I have like f double prime of x is 2. So this unit, we really are going to focus on just like finding derivatives. We won't really get too much into the applications because before we can do the applications, you do have to be really, really comfortable with just finding the derivative. So today's notes, we're just going to run through a bunch of rules we have and then kind of see where we're at. The first rule that we have is called the basic power rule. All of these rules, again, are on that handout you can print out, or you can follow along in the notes, or you can kind of go back to that page at the top of the notes later and fill it in. But the basic power rule is going to be used when you have x raised to a number, and n is going to have to be a number in the exponent, so not something like x to the 2x, but like x to the third, x to the fifth, and so on. And the derivative rule we have there is to take the derivative of x to the n, the coefficient comes down in front, and the new exponent is going to be 1 less than what it was originally. So as an example, if I say my function y is equal to x to the 7th power, the derivative of x to the 7th power would be that 7 is going to move down as a coefficient in front, and the new exponent, 7 minus 1, is going to give you 6. You might be asking yourself, you might not be asking yourself, but you might be asking yourself, where is this really coming from? Two ways I can kind of show you where it's coming from. So we started off looking at this unit, looking at the graph of a function and then drawing in its derivative. Well, we look at y is equal to x to the 7th. That is an odd power, so we know it has more of like that S shape to it. And x to the 7th ends up looking something like this. That is my original function. And if this was an example of a problem that we were doing yesterday, I would say, hey, let's graph the derivative of that. Well, if I'm looking at this problem that x to the 7th, it is always increasing. So the derivative is always positive, but it switches from being concave down to being concave up. So if I go to actually graph this problem, we have this is going to be the derivative I'm drawing. So it still has positive slopes, but it's concave down, so the derivative would be decreasing. And then the function is still increasing, but now it's concave up, so the derivative would also be increasing. That derivative that we drew is exactly the equation 7x to the 6th power. The other place where these rules are coming from are the traditional definition of the derivative. And so you might remember we said that f prime of x is defined as the limit as h goes to 0 of f of x plus h minus f of x all over h, and that is the traditional definition of the derivative. Well, if we evaluate this with our function being x to the 7th. Like I'm not going to do this one because it's a very gross one to have to simplify. But if I were to go to simplify this, so f of x, we're going to say is this function. That's what we want to take the derivative of. So I have the limit as h goes to 0. There's x plus h minus f of x all over h. Really gross to FOIL out, but if you FOIL that out, simplified, cancel some things out, and reduced it, you would get 6x, try that again, 7x to the 6th power. And we'll look at an example later on when actually you can kind of prove it to yourself that that's where it's coming from. But this is also where like you didn't realize you were doing a derivative when you were doing limits, but some of those limits questions were actually derivatives. You just didn't know it at the time. So we have the basic power rule. The next rule we have is the derivative of a constant. A constant is anything that's a number. So 5, 6, -10, pi, e, anything that's not changing and constant. And the derivative of a constant is 0. I think this one is pretty easy to justify to yourself why the derivative of a constant is 0. So if I take the derivative of y is equal to 4, y equal to 4 is just a horizontal line at 4. Well, we know that the derivative is the slope. What is the slope of all horizontal lines? The slope is 0. Well, we know that the slope is the derivative. So literally the derivative is always equal to 0. So here's what the derivative would look like. The derivative of 4 is 0. So that's why, but again, the rule that you want to have memorized is 0. And I probably should have emphasized this earlier, but I do say memorize. There are no formula sheets on the AP exam. You will want to have these formulas memorized. So then we have other rules. We have the derivatives of 2 of our trig functions are going to be considered basic, and that's going to be sine and cosine. And in the notes, I went ahead and put a graph of sine on here, because I think if you were to sketch the derivative like we did yesterday, so this is like f and we want to graph f prime, it makes sense why the derivative of sine is what it is. So looking at this, this is the graph of sine, and I want to be able to graph its derivative. Well, we know the derivative is equal to 0 whenever sine has a horizontal tangent. Sine has horizontal tangents at pi over 2, 3 pi over 2, and then we can also go backwards as well. And then if I'm looking at this graph, I see that's kind of increasing, decreasing, increasing, decreasing, and there's some concavity to it as well. So I'm going to go ahead and start at like the negative pi over 2. So looking at my graph, I see that it is increasing and concave up. Then it switches to increasing and concave down, but it's still positive. Then the graph is decreasing and concave down. Then it's decreasing and concave up, so my derivative will be going up. And then this last section is increasing, so a positive derivative, and it's concave up, so the graph will be increasing as well. And I can repeat that shape going across. You might be able to kind of look at this visually and like right at 0, if you drew a tangent line, it looks like the slope is at 1. I kind of knew it would be, so I went ahead and put that slope literally at 1. So this graph in blue is literally the first derivative of sine. Looking at that graph as blue, what do we know that the equation of that blue graph actually is?
Sine of x like minus pi.
Make it even simpler.
Cosine?
I was going to say cosine.
Oh,
It's the cosine. So it is sine with a phase shift, but directly it's even easiest to know that it is the cosine of x. So we saw in pre-calc that sine and cosine are pretty much very closely related. They're both like on the unit circle. The derivative of sine is literally the cosine graph. And so you can probably assume the derivative of cosine also has a very similar rule. The derivative of cosine is related to sine. So I'm going to go ahead and graph the derivative again. So we know that whenever the graph of cosine has a horizontal tangent, its derivative is equal to 0. And then starting at 0, I see that it is decreasing all the way to pi, but it switches from concave down to concave up, but it is decreasing the whole time. So when I go to graph this derivative, it's decreasing and then increasing. The function cosine is increasing, so we have a positive derivative. And then we can repeat, kind of going the other way. That is the derivative of cosine. What does it appear the derivative of cosine is?
Negative sign.
Negative sign. So if you remember, sine normally starts by going up first. This is going down first, so it is negative sign. One hint I'll tell you, like we're not looking at all the trigs today, but any of your co-trig functions, cosine, cosecant, and cotangent, they all have a negative derivative. Whereas all the ones that don't have a sine, tangent, and secant, they will have a positive derivative. So the derivative of sine is cosine. The derivative of cosine is negative sine. Next rules, I promise we'll look at some examples eventually, but lots of basic rules to kind of pass out to you. The next rule we have is a constant multiple. This is like when you have a coefficient in front of a function. When you have a coefficient in front of a function, that coefficient comes straight across, and then you just take the derivative of anything that comes after it. So if I have 4 sine of x, what is its derivative? Well, 4 is a coefficient, so it will come straight across, and we just learned the derivative of sine is positive cosine. So we have the derivative of 4 sine of x is 4 cosine of x. Last rule we have for today is the general power rule. The general power rule basically combines the power rule with the constant multiple rule. So this is going to be where you have like x raised to a number but a coefficient in front of it. So if I have the derivative of a x to the n, that a is a coefficient, so it's still going to come straight across. The exponent is still going to come down in front, joining the coefficient, and we're still going to subtract 1 from the original exponent. So for your example, if we have y is equal to 5x to the 7th power, its derivative, that 7 is going to come down in front with the 5. The new exponent is a 6, which we can just simplify to be 35x to the 6th power. To expand that a little bit further, we can also think about what happens when there's more than one term going on. For example, get a pen that I can write on it. If I have y is equal to, we'll say 4x squared plus 2x minus 3. To find the derivative of that, you just take the derivative of each term. So you just basically apply the rule to each term. You have to be careful. It doesn't work if you're like multiplying 2 things or dividing 2 things, only when you're adding or subtracting. So if I have y is equal to 4x squared plus 2x minus 3, and I want to find its derivative, first step would be to find the derivative of 4x squared. What's going to be the derivative of 4x squared? Well, that 2 comes down in front. And so we have 8x to the 1st power. And then it's plus, we want to do the derivative of 2x. What is the derivative of 2x going to be?
2. Just 2.
Just 2. So some people might think, okay, so I have 2x and I want to take the derivative of it. So let's see, that is a 1, it's going to come down in front, and that's x to the 0th power, which is just 2. I think it is a lot shorter just to think about 2x is a linear function. The slope is 2, and we know that slope is the same thing as the derivative. And then the derivative of negative 3 is going to be what?
0.
0. So I'm not going to include it because it's going to go to 0. So the derivative of that function would be this. So for some other examples I have already prepared, oftentimes we have problems that are power rule problems, but we can't do the power rule, or we don't clearly see it's a power rule until we rewrite it. So I have 5 examples here. Some of them you might be able to do without rewriting, but I'll kind of show you what I mean by rewriting. And I just have 2 more slides after this one. This first one I have y is equal to the square root of x. That's technically going to be a power rule example, because how can I rewrite that problem to see the power?
X 1/2.
X to the 1/2. And then we can easily take the derivative, so the 1/2 is going to come down in front. Subtract 1, make sure you always subtract 1. 1/2 minus 1 is negative 1/2. And you're more than welcome to leave your answer like that. I will say if this is a multiple choice question on the AP exam, they will often simplify their answer. So you can simplify it by getting rid of that negative exponent by sending the x to the denominator, which then you can also go back and write it as 1/2 square root of x. All 3 of those answers are equivalent and equal to each other. So like one is not more correct than the other. This second one, some things about derivatives. If you are dividing something, you just can't take the derivative of each part. So you can when you're adding or subtracting terms, but not when you have terms being divided or multiplied. So I have y is equal to 5/x, but I'm telling you that you can also use the power rule for that one. How could you rewrite that one so you can more easily use the power rule?
5x to the negative 1.
5x to the negative 1. So you can just pull it up out of the denominator. Now we can take the derivative. So the negative 1 is going to come down in front, giving me negative 5x. Negative 1 minus 1 is negative 2. That answer is perfectly fine. Or you can send the x to the denominator to have a positive exponent. Make sure if you're moving your terms around to get a positive exponent, you leave that negative 5 in the numerator because it didn't have a negative exponent attached to it. And then this last one on here, I don't think anyone in this class would be confused by it, but I'll go over it just in case. X/5, a lot of students think about that as being like a quotient, but just know that if we see y is equal to x/5, that's the same thing as saying 1/5 of x. And we know that the derivative of 1/5 of x is just going to be 1/5. Again, that is using the power rule, but also a nice little thing that the slope of this function, it is a linear function, is 1/5. Its slope is always 1/5. So it makes sense that its derivative is also going to give you 1/5. Questions on those examples? Or on anything? I feel like I've been talking really fast today, but any questions on anything? All right, before I give you a classwork assignment, I did want to give you this slide. So I think one thing that helps, especially as we're just adding to like our tool belt of how we find derivatives, is just also being able to recognize of like, do you have the skills to take the derivative now, yes or no? So obviously some of you might have already learned some different derivative rules in other classes, but based off of what I have taught you so far today, we're going to go kind of question by question and figure out if we can take the derivative yes or no. Now I'll kind of tell you if we will be able to do it eventually. This first one where I have y is equal to x plus sine of x, do you have the skills to take the derivative of this function? Yes or no? Yes, so those are just 2 things being added. The derivative of x is just 1. The derivative of sine is a rule you've memorized. The derivative of sine is just cosine. This second one, do you have the skills to be able to take the derivative of this one yet?
Yes.
Yep, it's just a constant multiple. So I have y prime is equal to 2 carries across. The derivative of sine is positive cosine. This second one, it looks like you might have the rule for it, but technically you don't. So we have the constant multiple rule. That is not a constant multiple, so this one is not yet. We're actually going to learn how to do this one tomorrow. And then this last example is also one where we don't know how to do it. So we've memorized the rule for the sine of x, but the sine of 2x is something different because we have something inside the function. This example we're actually not going to learn until after your quiz. So we actually have a ways to go before we can get to that problem. But those first two are definitely examples that you can do. So to finish up class, I do have like a classwork activity I want you to do, but I did want to talk about the homework first, which I have up here. So your homework, it is from the textbook. I know not everyone picked up a textbook, so I did scan in the textbook page and put it into OneNote for you. iReady is still a thing that's existing. You know it's not due until next Friday. Please try to work on that sum, especially if you haven't started it yet. Homework 1, hopefully you have finished, especially since I only assigned odds. Do the evens though, if you need the more practice. If you're struggling with those graphs, definitely get with me during office hours so we can kind of work on those together. The homework I'm assigning tonight, again, you can access this in OneNote. I scanned in the page for you. M4 just means multiples of 4, so I don't really know why I started at 6 there. That doesn't make sense. Probably should have started that at 8. But 8 through 24, multiples of 4, and then 44 and 48. That homework honestly shouldn't take you too long to do. Most of the work is going to be involved of like rewriting it so that you can use like the power rule and then just making sure you have those trig rules memorized. As a classwork assignment, what I want you to do is for us to be able to connect this back to what we know about limits. I am going to adjust it a little bit. So I have 3 problems up here, pretty straightforward problems. And for all of those problems, I want you to just find the derivative of it. So use your rules to find the derivative of it. For just one of them, so I don't want you to do it for all of them, but for just one of them, I want you to set up a limit using the traditional definition of the limit, and then evaluate that limit like you would back in Unit 1. And what you should see is that whichever one you pick, when you set up that limit using the traditional definition and simplify it, the final answer you get should be the answer you got when you did it using the rules. And I want you to do that just so you can kind of see where these rules come from, but then also too, just to kind of appreciate that these rules exist so that we don't have to do limits over and over and over again for these problems. But go ahead and take a moment. I'm going to stop the recording at this point because I just want to give you some time to work on it. But go ahead and take a moment to work on those 3. First, find the derivative, and then pick one of them to plug into the traditional definition of the derivative and simplify it. And basically, when you do the traditional definition, that first one's going to be a lot of foiling. The middle one is going to be canceling out some fractions, and that last one will be an example with rationalizing. But again, I think you only need to do one of those, and you'll get the benefit that I want you to from it. But I'm going to be quiet for a second to give you a chance to try those 4 tasks for me.